Okay, so let's start again from the here iron carbon equilibrium diagram. And to understand
Okay.
these diagrams, I used to say that we have to understand the microstructure of steel. Okay, so steel,
Okay.
the percentage of carbon when varying from 0 to 2.1%. But if we talk about the start of the microstructure, when we melt the iron itself, so its melting point
Hmm.
is around 515-38. So this is though in usual practice about this or beyond this, there is no use to discuss about this. I mean, the mechanism of developing of the microstructure up to that temperature. But once we cool the material after this reaching this point with different
Hmm.
concentration of steel, I mean sorry, carbon, then there is a difference happens into the microstructure of steel. So the very first
Yes, sir.
structure that we are considering, that is austenite, and the testonite, that austenite structure is the microstructure of iron carbon alloy in which iron is in FCC form. FCC form is the this one which I told you yesterday. यहीं पर I would like to tell you something. तो
Okay.
में क्या है कि अभी मैंने यहाँ पे दिया है 7. It forms in iron carbon alloy above 727 to 1500 डिग्री सेंटीग्रेड. यानी
Hmm.
कार्बन परसेंटेज पे मान लीजिए we take just for example we take 0.76% of carbon. Okay, so
Okay.
and if we heat this, then at
Hmm.
after reaching 727 degrees centigrade,
Hmm.
we will get this austenite structure, right? Similarly, austenite structure अलग अलग पॉइंट्स पे हमको मिलेगा, जैसे यहाँ भी है ये. These are the
Yes,
points
sir.
from where austenite structure will be formed.
Yeah.
And if we come from the top, then definitely it will start from this temperature line. यहाँ से होगा, है ना? तो ये टेम्परेचर
Yes, sir.
अराउंड 1500 डिग्री सेंटीग्रेड होता है. तो 1500
जी.
टॉप में है और 727 बॉटम में है.
बॉटम में.
ठीक है. और डिफरेंट
ओके.
इधर जाएंगे तो टेम्परेचर अलग है, इधर आएंगे तो टेम्परेचर अलग अलग होंगे, है ना? मान लो इस पॉइंट पे
Hmm.
टेम्परेचर तो ये हो जाएगा, ऐसे हम लाइन ड्रॉ कर देंगे तो विल गेट डिफरेंट टेम्परेचर लाइंस, है ना? तो
Yes, sir.
अभी इम्पोर्टेंट बात यहाँ पर क्या है, वो ये है कि पहली बात तो कह रहे हैं कि ये जितना भी स्ट्रक्चर होगा ऑस्टेनाइट का वो एफसीसी टाइप का होगा.
जी.
ये हमने एफसीसी बना दिया. ओके. अभी एफसीसी का मतलब है कि ये जो एटम्स है ना, ये एटम्स किसके हैं?
जी.
कौन से मटेरियल के एटम है ये? मेटल
ये
के
तो
हैं,
आयरन है.
आयरन के हैं.
आयरन.
करेक्ट,
यस,
आयरन
सर.
है. ओके. अब इसका मतलब इस स्ट्रक्चर में अगर इसी स्ट्रक्चर ऐसा स्ट्रक्चर बनेगा एफसीसी, तो कार्बन
जी.
कहाँ जाएगा? कार्बन इसका मतलब इसके आसपास इसके आसपास होना चाहिए, है ना?
जी.
तो
जो
एक,
वैकेंट जगह है उसमें ये
हाँ, जो वैकेंट
फिल
जगह
हो
है,
जाएगा.
वहाँ
जी.
होना चाहिए. यहाँ पर इम्पोर्टेंट बात ये यहाँ पर याद रखने की है, बिकॉज वी आर
जी.
टॉकिंग अबाउट द स्टील और द आयरन कार्बन
Hmm.
alloy. So we must know that the what is the dimension of this cube, या हमें ये पता होना चाहिए कि अगर हम बात करते हैं तो ये अगर ये पार्ट आयरन का है तो ये आयरन
जी.
का इतना पार्ट रेडियस आयरन का होगा, isn't it? है ना? और
यस, सर.
ऐसे ही ये होगा
Hmm.
और ये होगा. आप ऐसे डायगोनल ले लेते हैं तो ये डिस्टेंस होगी, है ना?
Hmm.
तो जैसे हम इसका फेस सेंटर्ड क्यूबिक का एफसीसी का एटॉमिक पैकिंग फैक्टर निकालते थे, तो वो एपीएफ
जी.
कितना आता था? 0.74.
0.72 शायद. 74, सॉरी.
ओके, कोई बात नहीं, और इजी है. Look, अभी क्या है कि इसका मतलब है इसमें जो हम मैक्सिमम 100% भी अगर इसको हम ऑक्यूपाई कर देंगे यूनिट सेल को, तो वी कैन
जी
ऐड मैक्सिमम ऑफ 0.26%। हमारे पास मैक्सिमम स्पेस 0.26% ही तो है।
जी
तो कार्बन अगर पूरा पूरा, अच्छा अभी क्या है, अब अगर हम एटॉमिक रेडियस की बात करें तो आयरन दैट इज Fe का हमारा जो रेडियस है, एटॉमिक रेडियस है, वो कितनी होती है? इट इज व्हाट आई नोट इट डाउन दिस,
uh,
इट इज अराउंड 0.124, ओके, नैनोमीटर, पॉइंट
0.124 नैनोमीटर।
नैनोमीटर। तो इसका मतलब जो अगर हम एडजेसेंट साइज की बात करेंगे तो 0.124 ही हो जाएगा, 0.124 ही हो जाएगा। इसके बीच में जो स्पेस है, इस स्पेस
हम्म
में तभी एटम आ सकता है जो रेडियस अगर उसका डाया इतना है,
जी
राइट। और वो हमारा क्या है? कार्बन। कार्बन का रेडियस क्या है? कार्बन का एटम का, कार्बन के एटम का रेडियस है 0.071
पॉइंट
नैनोमीटर, ओके। तो ये एक
ओके
इम्पोर्टेंट बात थी जो हमें ध्यान में रखनी है, ठीक है, ओके।
ओके सर।
यानी कि अगर हमारा ये डिस्टेंस जो है इतना यहाँ हमारा होगा कि कार्बन का, अभी ये रेडियस है, इसका
जी
डाया कितना हो जाएगा? मल्टीप्लाइज 2, so that will
हाँ
become
7 to the
2 or
4
4,
पॉइंट 4 to
0.142,
4 यस सर
0.142। तो दैट मीन्स
यस सर
व्हाट, ये जो एज है हमारा, ये कंप्लीट जो एज है, जो डायमेंशन है,
हम्म
ये किसके बराबर होनी चाहिए? ट्वाइस ऑफ द रेडियस ऑफ आयरन, इधर इधर प्लस
ट्वाइस
ट्वाइस ऑफ द
रेडियस ऑफ पावर
ट्वाइस ऑफ द
है
रेडियस ऑफ कार्बन,
यस सर
कार्बन एटम। दिस मस्ट इक्वल्स टू ए। तो क्या होगा? एटम कंप्लीटली हमारा साइड में इसमें आ जाएगा। एंड वी
जी
हैव, you know how many space are there? 1 2 3 4, then 5 6 7 8 9 10 11 12, okay. That is possible if it will be, if the dimensions will be like this. So that is the reason कि जो solubility है कार्बन की,
हम्म
कार्बन की solubility is maximum in austenite form,
ओके
understand? देखो कार्बन
ओके
की
ओके
मैक्सिमम सोलिबिलिटी कहाँ पर है? ऑस्टेनाइट में है। क्योंकि अल्फा, अभी जब हम बात करेंगे, अभी यहाँ से हम आगे चलते हैं,
हम्म
नेक्स्ट में देखिए आप, फेराइट, नेक्स्ट स्ट्रक्चर हमारा फेराइट है, ओके। ऑस्टेनाइट के बाद हम
जी
बात कर रहे थे फेराइट की। फेराइट, फेराइट में फेराइट में अगर आप देखोगे तो कार्बन का परसेंटेज देखिए, ये फेराइट है, दिस वन, कैन यू सी दिस?
यस सर
ये वाला पार्ट है, देखो। अगर मैं यहाँ एक पॉइंट नाउन करूँ, यहाँ पॉइंट 0.022 है, यहाँ पर
जी
400 लिखा है, तो बेसिकली ये वाला
जी
पार्ट है जिसमें अल्फा फेराइट हो सकता है। तो कार्बन का मैक्सिमम परसेंटेज कितना हो रहा है इसमें?
0.022
0.022, ठीक है।
यस सर
जबकि अगर आप ऑस्टेनाइट देखेंगे तो ऑस्टेनाइट मैक्सिमम परसेंटेज कितना है?
0.76 नो सॉरी 2.1
2.1, करेक्ट।
यस सर
तो अभी देखो,
यस
सेम मेटल है, बट
जी
द कार्बन परसेंटेज इज वेरिंग ड्रास्टिकली। Why this is
जी जी
possible? Why this is possible? This is possible because of the structure, base structure. क्यों? यहाँ देखिए आप, जबकि यहाँ पर बॉडी सेंटर्ड क्यूब है ये,
जी
इसका एपीएफ कितना होता है? इसका एपीएफ होता
5
है,
टू शायद 0.52 आई थिंक
नो नो 0.68 होता है, ओके।
ओके
कोई बात नहीं, दैट कैन बी फाइंड आउट, सिंपली उसको हम फाइंड कर सकते हैं। अभी क्या है, देखो इसका एटॉमिक पैकिंग फैक्टर कम है, यानी कि स्पेस इसमें ज्यादा है। इसमें
जी
स्पेस कितना हमारे पास कितना है? 32% स्पेस हमारे पास,
32%,
जबकि उसमें कितना था 26.
26.
Even then, carbon cannot be added more into this BCC cell. Understand?
Yes, sir.
From the diagram, you can see only 0.022%. इसका मतलब क्या है कि 0.022% तो इसके अंदर आ जाएगा. Okay? Where will be the rest? Rest will form Fe3C,
Cementite.
which is called cementite. So this structure is used to form the alpha ferrite forms by the slow cooling from austenitic structure, which can begin with a temperature in 912 to 727. 912, this temperature, 727 is this temperature, this one. इतने पर स्टार्ट हो सकता है से इतने तक. Okay. Alpha ferrite is evident at room temperature. अल्फा टेम्प जो आपका ये स्ट्रक्चर है, रूम टेम्परेचर मिलता है हमें, और इसमें जो मैक्सिमम जो हमारा कार्बन का परसेंटेज है, दैट कैन बी अप टू 0.02%. ठीक है, राइट. अच्छा, क्यों इसमें कम, इसमें आपको बताऊं मैं, इसमें जो ये परसेंटेज ऑफ कार्बन जो हमारा ऐड होता है, इट इज assume that at every 500 unit cells occupy one atom. Okay, तो
500
यूनिट सेल्स, 500 यूनिट सेल में एक आएगा. वहीं पर अगर आप गामा आर्सेनाइड की बात करते हैं, वहां पर जो आपको पास वो था, जो स्ट्रक्चर था, दैट वाज काइंड ऑफ interstitially, the location of the atoms were in the state of interstitial. You know that there was imperfections you have studied in the second year, that are
Yes, sir.
point defect and line defect and
Line defect,
surface.
volume
So
defect.
interstitial
also.
defect was one of the point defect. इसमें क्या होता था, फॉरेन एटम या एक्सटर्नल कोई एटम आके स्पेस को ले लेता था. तो कार्बन एटम इन ऑस्टेनाइट dissolves into iron in that way, interstitially. Okay.
Okay.
Okay. Or in BCC, carbon atom can dissolve only 1 per 500 unit cells, maximum up to 0.02 weight%. Okay. And that means what? कि जब इसको हम कूल करते हैं ऑस्टेनाइट पोजीशन से, from austenite to any temperature at any combination, when we cool down the material or the metal, so what happens, there will form 0.02% of BCC structure, that will be called alpha ferrite. Okay. Plus rest will be cementite, that is called Fe3C.
Fe3C. Okay.
So here what I was trying to tell you is that there are two structures, alpha ferrite, delta ferrite. Alpha ferrite is evident at room temperature, but in case of delta ferrite, if we go to above side, this is the range where delta ferrite is there. It is starting around at 1538 degrees centigrade to 1400 degrees centigrade, and the carbon percentage may also vary from here to this, little bit more than the 0.02%. Okay, so this way we can understand how the iron has the structure of microstructure at various temperature, various concentration, and how that structure can be evident at the room temperature. Like in case of delta ferrite, we can have delta ferrite at room temperature, but it is possible when the iron will be having more than 8% alloying elements. You know.
Okay, sir.
You know, those alloying elements are maybe chromium, vanadium,
Manganese also can be there.
manganese and all. Correct. So once iron is having that alloying element, it is called high alloy steel. Okay, if iron is having that alloying elements in percentage of more than 8, then high
Yes,
alloy
sir.
steel, and it is it can sustain, or it can have the delta ferrite microstructure at room temperature.
Room temperature.
That's fine. So this was
Okay,
the
sir.
point
I
which
got.
I was about to discuss you today again, because it is little bit very much, I have given here yesterday also. I have shown you there are some uh, uh, BCC cell and FCC cell. Then what is the use to represent these cells over here? दिखाने का क्या मकसद था, and how I have given some sites where atom may be fused but
Yes.
may be located, but whether it is possible or not, depending on the dimension of the unit cell.
Unit.
The dimension of the unit cell is also known as the primitives, where this A, B, C, and alpha, beta, gamma angles are there as per the geometry of the structure. Okay,
Units.
so these two things were important to discuss over here, which was I was about to tell you. Now,
Okay.
the next was perlite, which I told you earlier. When yesterday we will discuss this one
Yes, sir.
also. I think there is no
Yes, sir.
confusion in this, and that structure is alternate layers or alternate laths of the cementite and alpha ferrite. Okay, so be remember, alpha ferrite is again alpha ferrite is this over this part that is having 0.02% of carbon, and cementite is F3C. This is written over here, and which are the laminar or let's say parallel laths of alpha ferrite and cementite. Okay, which is
Okay, sir.
called perlite. And the structure looks like this. It is name on the appearance of this structure. It appears like pearl. So that is why this
Pearl.
structure is known as the perlite.
Perlite.
Now coming to
Okay,
the
sir.
martensite. Martensite is a structure which forms when steel from austenite structure is cooled at a very fast rate. This is very
Sir.
important. It also depends how you are cooling the material. I told you that
Sir, very fast.
very fast means quenching kind
Very
of.
fast means quenching. Yes, sir. Yes, sir.
Yeah,
In quenching in water.
yeah, water, or maybe different bath, maybe
Maybe oil.
maybe brine
Yes, sir.
solution, maybe salt solution. But the major purpose is to let it quickly uh, uh, cool down.
Ooh. Yes, sir.
So to achieve this structure, the steel is heated above upper critical point line. Here is above upper critical line. Okay, I
Yes,
have
sir.
this one. Upper critical
Upper.
temperature. The steel is then quenched in salt, oil, or bath to a much lower temperature. 150 to 300 डिग्री सेंटीग्रेड पे आ जाना चाहिए. हमारा quenching इस तरह का होना चाहिए. Okay, so you can see from
Okay.
here, also. Upper critical
Mm.
temperature आपका ये हुआ, ये लाइन हुई.
1147.
Austenite, हाँ, yeah, it may be up to 1147 at this side, or 727 maybe at this side also.
Lower critical temperature.
But though it is a point when lower critical temperature and upper critical point temperature is coinciding. But 900 to 912 to 1147, right? And let's see this one. And what is this? What they said, that the steel then quenched in salt, oil, or lead bath to a much lower temperature, around 150 degrees centigrade to 300 degrees centigrade, and it is held till the
Yes.
temperature becomes uniform. It's important.
Yes, sir.
What exactly they did in heat treatment process? We heat the metal, we hold it,
Hmm.
and we cool it.
That.
This is,
Yes, sir.
but here you can see after reaching this temperature or this temperature, there is
Hmm.
what? हीट किया अपर क्रिटिकल टेम्परेचर तक, ठीक है, थोड़ी बहुत देर होल्ड किया होगा, देन वी कूल इट। लेकिन कहाँ तक कूल किया? 150 to 300 डिग्री सेंटीग्रेड, और यहाँ पे रोक लिया फिर से, तो इट इज होल्डिंग टाइम अगेन। Here was holding,
Yes,
here
sir.
is holding. Two holes are there. Till temperature, it is a very hard, ठीक है, and then it is cold. So remember this point. Okay.
Okay, sir.
It is a very hard constituent due to the carbon which is trapped in solid solution. इसमें क्या है कि कार्बन के एटम्स को मौका नहीं मिलता डिस्पर्स होने का, समय नहीं मिलता। जैसे मैं यहाँ बताऊं आपसे, ये ऑस्टेनाइट में ले गए आप इसको यहाँ, तो इसके अंदर कार्बन जितना भी होगा, इफ विल डू इट स्लोली, तो क्या होगा, कार्बन डिस्प्लेस होगा, क्योंकि जो हमारा स्ट्रक्चर है वो बीसीसी का बनेगा, है ना। अगर एटम को अपने आप पर छोड़ देंगे हम, तो व्हाट विल हैपन, the structure will form BCC type, delta ferrite will be formed. But what we are doing, we're not giving time to settle the atoms to get this BCC structure. That means it will make something other type of a structure. Okay?
Yes, sir.
तो कार्बन को जहां मौका मिलेगा, जैसे होगा वो वहीं पे एडजस्ट हो जाएगा. So that is why it is written. It is a very hard constituent due to the carbon which is trapped in solid solution. Solid solution हमारा यहाँ था, है ना, ऑस्टेनाइट में. जैसे आपने उसको बहुत साथ कूल किया, 170 तक टेम्परेचर तक ले आए आप, तो 150 300, तो वो ट्रैप हो गया. द ट्रांसफॉर्मेशन फ्रॉम ऑस्टेनाइट टू martensite occurs due to sudden diffusion less shear process. और आगे बढ़ो. The unit cell of martensite structure is slightly longer in one dimension and shorter in other as compared to perfect cube in austenite structure. Now see this diagram. This was austenite structure, FCC, initially. When the steel was heated above upper critical temperature. Okay. Right? BCC में कैसे आना चाहिए? It should like this. This is a body centered cube. Alpha ferrite. This is alpha ferrite. This is gamma austenite. Okay? अभी ये इतना फास्ट है ये प्रोसेस कि इसको मौका ही नहीं मिलेगा. Okay? So the structure will be a little bit of this type. What is the difference between this and this? This is also body center. This is also body center. But see what is the difference? The difference is of dimension.
Yes, sir.
एक तरफ इसकी डायमेंशन राइज कर गई,
एक तरफ रिड्यूस हो गई,
और एक तरफ ये कॉन्ट्रैक्ट कर गई. This one. So this particular structure of the martensite is called body centered tetragonal. Body centered tetragonal, BCT. Okay. BCT. So the unit cell of martensite is slightly longer in one dimension and shorter in other, as compared to perfect cube in austenitic structure. Even the temperature at which the transformation starts is known as MS and MF when the temperature is complete, final. The structure becomes final, MS and MF. So you will see again this A will not be equals to C. In martensitic structure, body-centered BCT is the excess carbon atom are trapped and unable to diffuse out. मौका नहीं मिलता, वो ट्रैप हो गया यहाँ पर, यहाँ ट्रैप हो जाएगा, यहाँ ट्रैप हो जाएगा, यहाँ ट्रैप हो जाएगा. Okay? Due to quench so quickly. That is why this microstructure is very hard and brittle. Always remember this.
Okay, sir.
If you see the just geometrical point of view, then this diagram will explain. This is what? BCT.
DCT.
Clear हो गया?
Yes, sir.
I hope it must be very much clear to you. So very interesting. Huh?
Yes, sir.
Okay. So this is what is Martin-Site structure, and these are
Okay.
some very important structures. Now coming to, now you can understand this is a diagram. Okay. You can see here from this it is gamma austenite in this whole region. When you will come to this is somehow gamma structure is there, as well as some this Fe3C are also formed, cementite. Okay, right? And
Okay.
finally, you move downside, you will see first of all austenite, then this, then this, then finally this kind of structure available that is called your ferrite and perlite, mixing of two. So this is somehow perlite, which I saw in another diagram also, right?
Yes, sir.
And these are the species, white species of this kind. These are Fe3C, cementite. Okay.
Okay.
Where is Fe3C? Fe3C is the lamellar dark lines of little bit of almost red colors or pink color,
Yes, sir.
and the space, white space between them, that is the alpha ferrite. And this is sometimes this is called as a proeutectoid.
Proeutectoid.
Yeah. Where is proeutectoid? This structure is proeutectoid. This one, this is forming. Okay, this part is, ये जो part है इस part को बोल रहे हैं ये proeutectoid, and ये जो हमारे tubes जैसे बन रहे हैं pink color के, these are Fe3C and
Cementite.
cementite, that is cementite, और उसके बीच में जो ये white space है, this is alpha ferrite. So alpha ferrite and the plates of cementite is known as perlite. This particular structure is proeutectoid, जिसमें क्या है आपका, जिसमें क्या है आपका ये this alpha ferrite. Okay, and this is how once you are moving down from austenite and cooling it, so at various temperature you are getting different microstructure. When the carbon percentage is between 0.76 to 0.22. And this steel is known as, when the carbon percentage is less than 0.76 is known as hypoeutectoid.
Hypoeutectoid.
And you will see another example in this diagram. Here again it is a microstructure of austenite. Cooling down it, so you are getting this kind of structure. What is this? Fe3C and gamma. Okay, because Fe3C, this is here, and sorry, this is austenite, gamma is austenite will be there, and Fe3C, after this, everything which will form over this side, it will be Fe3C cementite. So gamma, austenite plus cementite structure will be available over here. This is here. Gamma, this austenite and cementite, right? You further cool it at after this temperature, 7 to lower critical temperature, you will get the diagram of the microstructure of this kind.
Okay, sir.
Okay. Again, you will get the perlite, you will get electroid Fe3C and proelectroid Fe3C. The structure will known as perlite and cementite.
Cementite.
Here was perlite and ferrite.
Right.
Okay, so that means here you will get perlite and Fe3C.
Cementite.
cementite. Okay.
Okay.
So this way
Okay.
we come to understand how the this iron carbon diagram is plotted, how it is understood, how the structure changes, and how the properties are related with that microstructure. And the microstructure is also influenced because of the alloying element present in the uh, iron and carbon. Okay.
Oh.
So this way we can better understand the iron carbon equilibrium diagram. Okay.
Hmm.
And with the help of this diagram, we can understand very well that is a heat treatment process.
Yes,
Okay.
sir.
So what is happening basically in heat treatment? What is happening? It is happening that we are heating the metal up to a certain temperature. Okay. After that, uh, certain temperature, heating the metal at that certain temperature, now we are trying to control the cooling rate. That cooling rate decides again, it will give time to settle down the carbon atoms into the uh, basic unit cell of the iron, which is FCC and BCC.
I see.
BCC, that is at alpha ferrite, BCC, that is at delta ferrite, and FCC, that is at gamma, that is austenite. So
Yes.
some of the carbon atom fuse or resides inside the cube at the depending of the, I mean, adjacent sides or the space between two atoms at the sides, or sometime it can trap inside the cube as interstitial sites. That time definitely the iron atom will be displaced out, and there will be the possibility of making the bond between iron and carbon separately, that is called Fe3C. That is also shown over this side. That is, if the percentage of carbon in iron is more about 6.7 or up to 6.7 from
Hmm.
2.14 to this, then the at 6.7%, the complete structure will be of cementite type of structure,
Yes, sir.
that is
Okay.
Fe3C. So this is how it is different to study iron carbon equilibrium diagrams, particularly at this time when you are taking the course as heat treatment process, and the same diagram we have studied or we have analyzed when we were studying material science and engineering. Okay, so this
Okay, sir.
is how we have to understand this particular diagram, the microstructures, and then
Hmm.
it will become very easy to let understand the various heat treatment process, right?
Okay.
Which is our basic purpose to study this subject. So there are certain type of heat treatment processes, like annealing is there, then hardening is there, tempering is there, normalizing is there,
Normalizing is
right?
there.
And now we will go into the detail of these heat treatment process, that how annealing is different from hardening, how hardening is different from tempering, how tempering is different from normalizing, and which particular process is suitable for which particular steel. Maybe if any treatment process is favorable with the low carbon steel, maybe the same cannot be favorable to the high carbon steel or tool steel or medium carbon steel, right? So along
Yes,
with
sir.
the steel having other alloying element also,
Hmm.
I have just discussed before, chromium, vanadium, tungsten, molybdenum, and so on. So let us
Okay.
go inside the heat treatment process one by one. That is just take annealing. So what is
Okay.
annealing? Annealing process is, it is the process of heating the metal above say 50 degrees centigrade upper critical temperature. So now we understand, because we have gone through this diagram. Now we have understood that where is the upper critical temperature and where is the other
Lower
input
critical temperature.
lower critical temperature
Yes.
and all. So as per this, we have to heat the metal 50 degrees centigrade above the upper critical temperature. So we'll see, as I've given you the diagram in parallel also. So this is basically that line which is upper critical temperature line. Okay, 50 centigrade above this. Okay, so if we think that upper critical temperature varies from 900 to 727, and here it is maybe up to 2000, I mean Fahrenheit. This is in Fahrenheit. So if we'll see into this diagram, so we'll see that 912, 727 degrees centigrade, and this is 1147 degrees centigrade. So annealing can be performed once the temperature will be more than 50 at any state. Suppose we talk about this point, 912 से ऊपर ले स्टील, यहाँ कोई हमारा स्टील है 0.76 का है मान लीजिए, जिसमें 0.7% का यू टेक्टेड स्टील है, तो 50 डिग्री सेंटीग्रेड above then 727 plus 50, it will become 777. So we'll heat the metal up to certain here. If we heat the metal up to this, it will be the initiation part of the annealing. Holding it there until the temperature is uniform so that all the distortion or stress is removed. This is the basic purpose of this process. जितने भी डिस्टोर्शंस हैं या स्ट्रेस रेजिड्यू कर गया है उसको रिमूव करना हमारा मेन मकसद है. उसके बाद दूसरा पैरामीटर क्या है? तीसरा पैरामीटर, पहला 50 डिग्री ऊपर लेके जाएंगे अपर क्रिटिकल से, देन उसको वहां पे हम इतने देर तक रखेंगे ताकि हम अश्योर हो जाएं कि स्ट्रेसेस रिमूव हो गए हैं या जिस तरह के भी डिस्टोर्शन है तो वो खत्म हो गए हैं. नाउ वी विल कूल एट ए स्लो रेट 18 to 40 डिग्री सेंटीग्रेड पर आवर. ये रेट हम सेट कर देंगे, इस रेट से हम उसको कूल करेंगे.
ओके ओके.
दिस वे रिलेटिव स्ट्रेसेस क्या करेंगे, वो सॉफ्टनिंग क्रिएट कर देंगे, और जब भी कोई मेटल सॉफ्टन हो जाएगा तो उसकी डक्टिलिटी बढ़ जाती है, तो इंक्रीज द डक्टिलिटी. जी, करेक्ट है.
यस सर.
और जब डक्टिलिटी बढ़ेगी तो क्या होगा, प्लास्टिक डिफॉर्मेशन भी उसकी बढ़ जाएगी.
जी.
प्लास्टिक डिफॉर्मेशन बढ़ जाएगी तो मशीनिंग और ग्राइंडिंग के ऑपरेशंस अच्छे हो जाएंगे. जी, ठीक है. And this is basically the main important objectives of this process, by which we increase the ductility, we make the material machinable, we make the material stress free.
Yes,
right?
sir.
And this way we can modify the property of the material by this particular treatment process. Understand?
Yes, sir. Yes, sir.
Okay. Now, so what were the prime objectives? Ductility increase करना है,
yes, sir.
better machinability करनी है, और forming operations better. देखिए डक्टिलिटी अच्छी होगी तो प्लास्टिक डिफॉर्मेशन बढ़ जाएगा.
Yes, sir. These things are interlinked. If ductility will be good, then
and it is when there will be no stress residue. कैसे होएगा? रिकवरी होगी, रिक्रिस्टलाइजेशन होगा, ग्रेन ग्रोथ होगा. मैकेनिज्म क्या है? दिस इज द मैकेनिज्म. रिकवरी मीन्स you are relieving the stresses. Recrystallization, the crystals are forming again, and the grain will grow. So these are the three stages. In first stages, that is what recovery. Softening of the metal is completed through removal of primary linear defects. Dislocations जितने भी होंगे उनको निकाल दिया जाएगा. And the internal stresses. Number one. Recovery occurs at lower temperature stage of all annealing process and before the appearance of new strain-free grain. Strain-free grains. Second stage में क्या करेंगे? Where the new strain-free grains nucleate, nucleation and growth होगा, recrystallization होगा ना, crystal बनेंगे अभी. Replace those deformed, उनको replace कर देगा वो, जो deform हो चुके already. healing हो जाएगी उनकी. If annealing is allowed to continue once registration has completed, then third stage is grain growth. What is that? The microstructure starts coercion, may cause the metal to lose a substantial part of its original strength. This can, however, regain hardening. Understand? So this
Yes,
is
sir.
how this particular process is executed. कैसे होती है, concept क्या है, objective क्या है, और variable parameters क्या है. Clear?
Okay.
Now,
Okay, sir.
what is mechanism? Mechanism क्या है? In annealing, atoms migrate in the crystal lattice and the number of dislocations decreases. देखो dislocations क्यों हो रहे हैं? Line dislocation. जब do you remember इस तरह से हमारा स्ट्रक्चर होता था और कहीं पे कोई लाइन ही मिस कर गए. So that time this was become the dislocation.
Yes, sir.
तो एटम्स माइग्रेट इन द क्रिस्टल. अभी ये एटम जो डिसलोकेट हो गए थे ये माइग्रेट कर जाएंगे जहां जरूरत होगी,
जी.
लीडिंग टू चेंज इन डक्ट. और तो उससे क्या होगा? डिसलोकेशन. देखिए डिसलोकेशन खत्म. जब एटम मेरे माइग्रेट कर गए सही जगह पर जहां उनको होना चाहिए था, तो डिसलोकेशन खत्म हो गया. डिसलोकेशन खत्म हो गया. दिस मींस व्हाट हैपन? परफेक्ट बन गया.
जी.
परफेक्ट हो गया तो उसकी डक्टिलिटी लीडिंग टू चेंज इन डक्टिलिटी and hardness as material cools it crystallize. This is the mechanism, है ना? The
Yes, sir.
process hot working or cold working after the annealing process alters the metal structure, so further retreatment may. तो अक्सर जितने भी हमारे प्रोसेस कोल्ड वर्किंग या हॉट वर्किंग या फॉर्मिंग ऑपरेशंस, ये भी जितनी मशीनिंग ऑपरेशंस हमारे होते हैं किसी प्रोडक्ट को बनाने के लिए, तो उसके बाद में उनका हीट ट्रीटमेंट करना जरूरी होता है. मुझे लगता है अक्सर तुमने देखा होगा गाँव में बर्तन चटक जाते हैं.
जी.
क्यों चटकेंगे भाई? क्यों क्रैक कर जाते हैं वो? इसका मतलब उनके अंदर रेजिड्यू स्ट्रेसेस रहते हैं, क्रैक रह जाते हैं, डिसलोकेशंस रह जाती हैं. उसका मतलब क्या है? वो लोकल कंपनीज वाले क्या करते होंगे? दे डू नॉट गो टू द हीट ट्रीटमेंट आफ्टर मैन्युफैक्चरिंग द प्रोडक्ट. क्योंकि हीट ट्रीटमेंट फर्दर करेंगे तो कॉस्ट बढ़ेगी तो महंगा हो जाएगा. महंगा होगा तो शहर में बिकेगा नहीं. कहाँ बेचेंगे? गाँव में जाके बेचेंगे. देखने में वो चमचमाते लगते हैं लेकिन दे पीपल व्हिच आर दे डोंट नो व्हाट इज द दे सी स्टील इज स्टील. उनको तो यही लगता है, isn't it?
Yes, sir.
जैसे गांव में और लोकल में जो गोल्डन का काम करने वाले होते हैं, ठीक है, तो दे यूज टू 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 use they used to use maximum copper or other elements into gold, and by that they their gold is not pure. So
Yes,
what
sir.
happens in that case? The normal people cannot understand. That is why वो पब्लिक को बचाने के लिए क्या किया गया कि चलो भाई हॉलमार्क देखो. अभी हॉलमार्क और वो सब चीजों में तो वही पड़ेगा ना जिसको अपनी वो बचानी है. अदरवाइज तो thieves are there, चोर लोग बैठे हैं, they can use very easily, and normal people cannot understand what kind of impurities may be there into gold or what may be the manufacturing defect in steel also. You can
Yes,
see
sir.
it's a very big काला बाजारी है इसमें. You can go to the market and you would like to purchase the steels. It will look same, but the steel of the branded companies will be costly one. Why it is costly? Because it is gone through all these processes. The life of the product is more. The actual property of the material is justified by their product. That is why it is costly.
Yes, sir.
Understand?
Yeah. Yes, sir.
So, and what is the role of thermodynamics in annealing? Annealing occurs by diffusion of atoms within a solid material. Diffusion of atom तो होना ही है. जब atom migrate करेंगे ना within a solid, so that the material progress towards the equilibrium state. Heat increases the rate of diffusion. This is the role of thermodynamics. Providing the energy, thermal energy needed to break bonds. Atom टूट के वहां से भागेंगे ना. The movement of atom has the effect of redistribution and eradicating the dislocations. Dislocations को हटा देंगे. This alteration to existing dislocations allow a metal subject to deform more easily, increasing its ductility. This is the role of thermodynamics. Heat. Okay.
Yes, sir. Okay.
Very clear. I think it must be very clear to you.
Yes, sir.
Then there is certain type of annealing, like it can be full annealing, it can be process annealing,
Processor.
it can be spheroidizing, right? So this can be also understood how they are different. What is full annealing as per the metric given over here? This process is very much favorable for low carbon steel. And of course, medium carbon steel, which experiences extensive plastic deformation. More ductile materials are these are. At the time of machining and forming operations, we require this. You know how we can ascertain the plastic deformation? This is the tensile test diagram, stress strain diagram.
Yes, sir.
You remember this?
Yes, sir.
Here is the elastic deformation, and here is the plastic deformation after fracture. So this is particularly this is responsible for the plastic deformation for forming operations, where you will apply the force and you will modify the shape of the material with the help of some forces and energies. The steel or alloy steel is heated 50 degrees centigrade above upper critical temperature A3 in case of hypoeutectoid steel. See hypo to form austenite phase and above lower critical temperature line in case of hypereutectoid steel. ये पॉइंट इंपॉर्टेंट है. देखो अभी क्या है, पहले क्या था, इसमें ऐसे था, इट वाज लाइक दिस, अपर क्रिटिकल टेम्परेचर पे था, बट हियर क्या है, लो, यहां तक तो गए हम हायर पे, कहां, हाइपोयूटेक्टोइड पे. वंस वी टेक द हाइपरयूटेक्टोइड स्टील तो हम लोअर क्रिटिकल टेम्परेचर पे चले गए. दिस इज द डिस्ट्रीब्यूशन लाइन, याद रखने की बात है. क्लियर हो गया?
Yes, sir.
Okay. This is the only
some.
Yes.
कहीं ना कहीं ये सारी चीजें सर पड़ी हुई हैं, तो थोड़ी बहुत दिमाग में है और फिर समझाने से और ज्यादा समझ में आ रही है, क्लियर हो जा रही है साथ ही साथ.
चलो वेरी गुड, वही मेरा पर्पज है. लेकिन ये इस तरह के डायग्राम्स के हेल्प से और अलग अलग से, दिस इज वेरी टिपिकल टू अंडरस्टैंड बिफोर इट, बियॉन्ड विदाउट इट, है ना. ओके, सो दिस वे इट इज इम्पोर्टेंट टू नोट कि जब आप अपर क्रिटिकल और लोअर क्रिटिकल, हाइपर और हाइपो को इस तरह से करेंगे तो देन यू विल अचीव, दिस प्रोसेस विल बी कॉल्ड एज full annealing. Okay. Sorry. Yeah. The furnace, अच्छा, and what is another thing? ये करने के बाद में, heat करने के बाद, the furnace is then turned off and both furnace and the steel cools to room temperature at the same rate. फर्नेस के अंदर ही आप फर्नेस को बंद कर देंगे, ऑफ कर देंगे और उसको ठंडा होने देंगे. The microstructure of the full annealed steel is coarse perlite, which is soft and ductile. Okay, so this is another point to remember.
Okay, sir.
Okay, now let's move to अनदर प्रोसेस एनेलिंग, उसको
प्रोसेस
हम इंटरमीडिएट एनेलिंग भी बोलते हैं, सुपर क्रिटिकल भी बोलते हैं, इन प्रोसेस भी बोलते हैं. This process is mainly suited for low carbon steel. That was for medium and low both, but it is mainly for low
लो
carbon.
कार्बन स्टील.
Normally used
Okay.
to say LCS also. The material is heated to temperature just below the lower critical temperature. See, now what we are doing, we are heating the material below this. इसके नीचे ही करेंगे, ज्यादा नहीं करेंगे. Temperature range for process annealing range from 260 to 760. 760. Okay, let's go back. It is a heat treatment cycle that restores some of the ductility to a product being cold worked, so it can be cold worked further without breaking. It is a heat treatment cycle that restores some of the ductility to a product being cold worked. Cold working करने के बाद में ductility कम हो जाएगी.
जी.
लो माइल्ड स्टील पर जब आप कोल्ड वर्किंग करेंगे तो what will happen? The ductility will break down, or you can say due to strain hardening, the hardness will increase. So by this particular method, what we did, we restore, वापस में हम उसकी ductility को restore करेंगे. As cold worked steel normally tends to possess increased hardness. I told you ना, hardness बढ़ जाएगी and decreased ductility, making it difficult to work. Process annealing tends to improve these characteristics. This is mainly carried out on cold rolled steel like wire drawn steel, centrifugally cast ductile iron pipe, etc. उन पे इसको किया जाता है. So very simple, just heat the metal and cool it so that the ductility may be restored back. Simply ऐसा बोल सकते हैं जैसे हम टेंसाइल टेस्ट में करते हैं कि उसकी इलास्टिक लोड तक हम अगर मटेरियल पे लोड अप्लाई कर रहे हैं सो दैट टाइम उसके बाद लोड को हटा लेते हैं तो व्हाट हैपेंस, it get the shape and size same back.
Yes sir.
Similarly it will happen over here also. Okay, so
Okay,
time is okay, so I think the time is over. Maybe another person will be waiting for the class. So that's all again today for here. We will start spheroidizing and normalizing in the next lecture. Okay.
tomorrow sir
I
lecture
mean
होगा.
next whenever it will be.
कल नहीं होगा शायद.
जब भी मेरा होगा नहीं, no, I don't have tomorrow, but in next lecture we'll discuss further other parts. So please go very precisely in this, है ना. बहुत आप अच्छे से इसको करो so that the question will be maximum asked. Very pointed question will be there because I think whatever the pattern of exam will be there, but from the point of view of the examinations, all kind of examinations, you need to study this very precisely.
Yes sir.
So this is all about. Thank you and keep safe. Enjoy your study. Take care.
Okay sir. Thank you.